So we are doing research on control applications for process plants. And here's a very simple example. We have here an industrial boiler where you can heat some fluids, for example, some chemicals. And then we have some pipes which give you, let the fluids into the tank. And we have some valves here which you can open and close. And then we have a sensor which measures the level in the tank. So how much fluid is in the tank. And the filling level is reported to a real-time controller. So we have closed loop control here, and the real-time controller sends valve opening signals, and then by that can regulate the filling level of the tank. And inside the controller, you have this control logic. It's written in an IC 61131.3. It's a Pascal-like programming language, and it's executed cyclically. So every 100 milliseconds, for example, it computes the values, so reads the filling level, and based on the algorithm, it then computes the outputs for the opening signal. So this is a very, very simple and very simplified example just to make the principle clear. And today we are deploying this on embedded real-time controllers, and the software deployment is quite fixed and static, so we cannot change that. And this gives us some problems. So what happens if we want to update the software, if we want to change the algorithm, but we don't want to interrupt the production? Because if we have to shut down the boiler and the entire process plant behind that, that's very expensive. It takes days to shut it down and bring it up again. And so it's very expensive. We want to avoid that. Today, it's often so that people don't change these algorithms too much because they're afraid of those updates. But in the future, we want to make it much more flexible. So that was our question. So we also looked into literature, what is already available on dynamic software updates. And there are a few works which are also concerning these real-time applications. However, they are all predate the container movement, so they have no container deployment, and they can do no updates of the underlying execution runtimes and the operating system, because that's also something we want to improve here, that we can update the, so to say, the firmware of the entire controller without interruptions to the system. Then there's also works on showing how you can have these programmable logical controllers in containers, without updates, just verifying that they actually work and execute with the right timing behavior and acceptable jitter. So these works we already have. And then from the other side, from the container orchestration engines and Kubernetes and so on, there are also a few works which deal with state replication. Because if you want to update something and you want to move to an updated container, then you need to replicate the state between containers. And there are a few works there which are not from the industrial automation domain. For example, there are ones for video streaming applications. So they have a little bit different context, and they have much more simple internal states. For example, they transfer just the position where you are in a video, and that's a very simple data. Good. So how do we approach that? Our contribution is we say we have a new form of deployment here. We have not an embedded real-time controller, but we have a Kubernetes cluster here composed of multiple nodes. This could be industry PCs, so hardened PCs that are equipped with a real-time operating system like Linux, and they run in a Kubernetes cluster and a Docker runtime, for example. And the idea is that we put the control software into a Docker container, and then at runtime, we can go from the original container to an updated container and do a state transfer. And once the state transfer is done, then we can switch off the old one and move to the next one. And our aim is to do that within one control cycle. So within 100 milliseconds, for example, so that the plant runs bumpless, interrupt-free, and you don't notice any changes here. But we can switch to an updated version and slightly change also the behavior here. Just some background, what is Kubernetes? So it's a cluster of nodes where you have one control plane and then several compute machines. So these are different servers. They have some management software from Kubernetes. Each worker node or compute machine here also has a kubelet and a kube proxy. And these pods, they encapsulate containers, for example, Docker containers. You might have also an underlying persistent storage and a container registry, so to actually pull software for updates. And you can run that on different infrastructures like bare metal directly, virtual servers, or private, public, and hybrid clouds. Currently, we are aiming more like for a virtual setup on premises. So this is not executed in a public data center, but rather in an on-premise little clustered data center, like a private cloud, at the location of the process plant or power plant. Then we use OPC-UA for the state transfer. That's the middleware that is used in industrial communication. It's basically client-server architecture. You have a server, and the server exposes a so-called address space. And these nodes here, they represent actual sensor values in the real world. For example, the filling level in the tank could be expressed by such a node. And then clients can come and register for subscriptions to those values, and then get live updates constantly from the values. You can also put control signals in here, for example, the opening level of a valve. So this allows you to interact with the entire plant. And we utilize OPC-UA also for the state transfer, because the protocol is deployed anyhow. So it's we just take the nodes and their current values and then transfer that to a separate OPC-UA server, as we will see right on. So to validate our approach, we implemented it using open source software. We use the Open PLC engine. You can also download that from the web. We equipped it with an OPC-UA server. It consists of an editor where you can click together control logic, either using this Pascal-like notation I showed in the beginning, or via these function blocks here, which is very common for automation engineers to use function blocks. And it also includes a runtime. The runtime also has a user interface displayed here on the right-hand side. And this shows you some live updating values like the fluid level and the configuration in the system. This is how our architecture looks like. So it's regular Kubernetes system. We have here the master, the controller nodes for Kubernetes. Then we have 2 worker nodes. This is simplified. In a real plant, there would be maybe a dozen of nodes or a couple of dozen of nodes where we run the software. And the control programs, they run now in Docker containers and Kubernetes pods. So we put the entire runtime into such a pod. Here we have also the internal state in there. And then we can start an updated version of that pod where the program is slightly changed, and we can then transfer the internal state with our Kubernetes operator here via the OPC-UA protocol. So operators are a customization mechanism for Kubernetes, so standard mechanism, and we just utilize that. So our operator, it monitors the running pods, and once it gets an update request, for example, from an operator or from the Kubernetes environment itself, because it wants to move the software between nodes, then it reads out the internal state, transfers it to the updated version, and then switches also over the input and output signals. The dynamic flow looks like this, very complicated here, but lots of steps. Essentially what it does, the Kubernetes controller, this operator, that it connects to both runtimes, then it pauses one of the runtime, or pauses both runtimes, extracts the internal states, and then transfers the state to the second runtime, and then it unpauses both. And these steps here need to be very, very fast. So we have this cyclic execution every 100 milliseconds. So maybe we need 10 milliseconds to compute the algorithms, and then we have an idle time of approximately 90 milliseconds. And in that time, we need to transfer the entire internal state. And the internal state can grow to hundreds of kilobytes or even megabytes. And then we need to be very fast here and need fast networks. So afterwards, we have both containers running, and then we implemented also a safety mechanism. So we verify the correct behavior. This is actually done manually. So an operator sits in front of the screen and looks like, is the output computed by the one engine the expected one? And only if that is correct, then we switch over from the original runtime to the updated runtime. And there's a button for that. It can also happen that it cannot be verified, and then we do a rollback and discard the updated container and roll back the system. Let's have a short demo on that. I'm just running this here. We see here a Kubernetes dashboard, which exposes you the pods and the containers running in the system. And I just want to highlight here, we have this Open PLC pod here highlighted. Open PLC, so there the engine runs, and it exposes the web port and port here, and we see the user interface, the dashboard of that, and we go to the monitoring. And there you see the engine is now started, but it has not been initialized. So we use an OPC-UA client to supply a set point to the algorithm to say, okay, let's fill the tank by 600 centimeters. And then the control algorithm kicks in, and you see the fluid level is slowly rising up to the 600 centimeters. And once it's there, then the controller controls the valves that regulate the input and output to keep the level at 600 centimeters. Yeah, so the state is reached now. We have speeded up a little bit. And now the controller tries to keep always the level. So now we want to update the whole thing because we have some changes in our control logic. And we do that by going to the editor and simulate that here by saying, okay, this less than block, we just exchange it with a less equal block because we want to make it a little bit more precise. And we reconnect the signals here to that block. And then we have new control logic, and then we can download that to a new container image and start a separate container up. That's what we do now. So an updated version of the OpenPLC runtime running this updated logic. So we have now both containers running here. You see on the left-hand side the original one with the current state, and on the right-hand side the updated one, which does not have this state. So it does not know yet that the level to maintain is 600 centimeters. Now we launch via the command line our state transfer program. And you will see then that this goes very fast. Now the state has been transferred, and the second engine has the same internal state as the first one. Now an operator can look at these values and say, okay, yeah, it looks like it also the new engine computes the correct outputs, and yeah, then we just rewire the stuff here. This is done here still manually, but it could be automated by the operator. And afterwards, we can stop the original engine. And yeah, then the new engine takes over the yeah, controlling of the fluid level in the tank. So much for the demo. And yeah, we also did a case study. So we looked at different systems. So we searched for a little bit larger system, and we found this liquid natural gas plant from Norway, which has like 18 controllers. So we looked at the control logic there, and it contained up to 100,000 internal state variables. So these variables are floats and integers and stuff like that. So basic data types. So we did some test applications based on the sizing that we found here in this plant. We didn't deploy our approach already in this plant, but first we did some experiments on how it would turn out. And then we measured the state transfer execution time. And in the beginning, I said, yeah, we need to transfer the state within the cycle slack time. So in below 90 milliseconds, if we assume 100 millisecond cycle time, which is yeah, typical for these processes here. So we see here on the x-axis the number of variables in the state transfer, and then on the y-axis the execution time. And then we did a lot of experiments and did 100 runs for increasing numbers of state variables. And we see here at 100,000 variables, we had a state transfer time of, in the average case, of 10.8 milliseconds. So this is well below our 90 millisecond target. So that's quite nice. And also, if you look at the worst case execution time that we experienced was like 14 milliseconds. And this is still sufficient, and yeah, probably also robust enough to have some remaining slack time in case there are any other interferences with the system. Yeah, we also measured a little bit deeper where the time is actually spent. Yeah, you see there are some spikes here depending on the communication, but maybe I don't go into details there. You can read up the details also in the paper. Yeah, to summarize, we did an approach to update control application at runtime, and we utilized yeah, containers and a container orchestration system for that. So essentially a Kubernetes cluster. We proposed a Kubernetes operator to monitor these control algorithms at runtime, and then allow also to do a state transfer so that we can switch over between instances. And we also measured then whether this critical internal state transfer time is below our target threshold. So this enables then to do dynamic updates of load control applications and avoid a plant downtime, because the process in the best time, yeah, should not experience any outages here or any interferences here. And this mechanism is actually quite interesting, because you cannot only use it here for updates, but also for rearranging the cluster, for example. If you want to move workloads from one node to the other node, you can use the same mechanism, even if you don't update the engine itself. And another thing is you can not only update the control program, but also the runtime engine, or even the operating system if you go to a new node. So it provides us a lot of flexibility with updating these kinds of systems. And yeah, we hope in the future that this becomes an integrated feature, and that more plant owners and automation engineers can utilize that to be able to optimize their plants much more dynamically. Future work is also to look into local shared memory state transfer. So far, we use a network protocol, which is still not optimal for very fast transfer times, but it was sufficient here in our case. You could also have some more sophisticated mechanisms to determine where to deploy the workloads if you have a freedom in the cluster. And then we also would like to look into resource-constrained devices, so new embedded systems and real-time operating systems like VxWorks. They have implemented recently also container engines, container runtimes for Docker, even on very resource-constrained and memory-constrained devices. So that could be something which we could also exploit, because in some situations you still need these embedded devices, and it could be a way to broaden the applicability of the entire approach. Yeah, with that, thank you very much for the attention, and I'm open for questions.